Hello everyone, my name is Vijay Shankar. I'm currently pursuing my Masters in Data Science from Liverpool John Moores University. My thesis supervisor is Dr. Dattatreya Parle. I'll be presenting my master's thesis. The topic of my thesis is comparative analysis of open source foundation large language models for finance through implementation. Let's get started with the introduction. Large language models, LLMs, are the latest and most exciting development in the field of natural language processing. LLMs have been trained on vast variety of data from multiple sources and have shown outstanding performance on different NLP tasks like text generation, text summarization, mission translation, and many more. The most famous implementation of LLMs have been in the form of ChatGPT. ChatGPT has been used by users across the world and has become one of the fastest growing applications, registering close to 100 million users within a couple of months of its launch. Now that we have established the effectiveness of LLMs, the next question is, how can enterprises in domains like medicine, finance, and legal adapt these LLMs for their specific use cases or applications? Research shows that LLMs which have been fine-tuned on domain-specific data outperform the LLMs which have not been fine-tuned. So these enterprises can perform fine-tuning to tailor these LLMs for their specific needs. Now the next question is, which type of LLM should be used? We have commercial LLMs and open source LLMs. Commercial LLMs requires the users and enterprises to pay for their usage. Commercial LLMs also requires the users to send their queries to their servers, to LLM servers to perform the processing, prediction, and to return back the results. This is particularly problematic from a data security perspective because we have finance domain enterprises like banks which have a strict regulatory framework in place which prohibits them from sharing the data outside of its network. Issues can be overcome with the help of open source LLMs. Open source LLMs can be hosted within the network infrastructure of their respective companies, and there is no additional cost involved with the usage of open source LLMs. Now that we have understood the advantages of open source LLMs, the next question is, which open source LLMs should these enterprises adapt? So this study is mainly focused on the finance domain. So the main aim of this study is to consider top open source LLMs, perform fine tuning on those LLMs, and to provide a thorough and comprehensive comparative analysis of the LLMs which were considered. So now that we have established the problem statement and background of this study, let's have a look at the aims and objectives. The first and foremost objective of this study is to develop an end-to-end programming framework which can load the data, convert it into a format which can be used by the LLM, perform the fine-tuning, and finally perform the evaluation. The next objective is to create instruction tuning datasets. Instruction tuning is a technique of describing the task in natural language and adding it to the prompt which will be used to fine-tune the LLMs. This technique has been shown to improve the performance, and hence it will be performed as part of this study. The next objective is to fine-tune the LLMs. The programming framework which was explained earlier will be used to load the config and optimal hyperparameters to fine-tune the LLMs, and this setup will be used to perform the fine-tuning. The final objective is to perform a thorough and comprehensive comparative analysis using the results obtained from evaluation. Now that we have seen the aims and objectives, let's have a look at the literature review. This study is mainly focused on the finance domain. So the main question is, which are the key NLP tasks which should be considered for this study? Based on thorough literature review, sentiment analysis and question answering tasks have been selected for this research. Sentiment analysis is a technique of determining sentiment of a particular text as either positive, negative, or neutral. Literature review shows that sentiment analysis plays an important role in decoding the market trends and guiding strategic trading decisions. Studies also show that sentiment analysis for finance domain is different from general sentiment analysis. For example, the word liability has a negative meaning in general sense, but has a neutral meaning with respect to finance domain. This shows the importance of fine-tuning for sentiment analysis task. So the next task considered is question answering. Investment research and analysis is an important activity in finance domain. It typically involves analyzing the financial reports, and these reports contain both tabular and text data. Question answering systems are usually used to extract the required information from investment reports. Since these reports contain both tabular and text data, this is a particularly challenging use case for the LLMs because of the difference in formats. In the general use case for question answering, it involves only extracting the information from text data. But in the finance domain, it needs to have the understanding, the question answering system needs to have the understanding to extract the data from both the general text and as well as the tabular data and perform the necessary numerical operations to arrive at the final answer. Now let's have a look at the key open source LLMs. Through thorough literature review of the evaluation results reported by the open source LLMs, three models have been selected for this research. Llama 2, Mistral and Falcon will be considered for this research, and these models will be fine-tuned and evaluated to provide a complete and thorough comparative analysis. Now that we have had a look at the literature review, let's have a look at the research gap. FinBERT was one of the earliest language models which was developed for finance domain. FinBERT considers BERT as the base model and fine-tunes it on finance domain data such as earning call transcripts and corporate reports. FLANG is an improved version of FinBERT which uses preferential token masking to achieve superior performance. Bloomberg GPT is the biggest LLM in finance domain and shows outstanding performance. However, the major drawback is that it's a commercial LLM and it suffers from the same disadvantage which was discussed earlier. The field of open source LLMs is relatively new, and existing studies focus on fine-tuning specific LLM on finance domain data. Literature review reveals that there are no existing studies which fine-tune multiple open source LLMs on finance data and present comparative analysis through evaluation. Therefore, this study aims to bridge that gap by considering top 3 open source LLMs, Llama 2, Falcon and Mistral, and fine-tuning all of them on financial data and evaluating them on important NLP tasks using appropriate evaluation metrics. The results of this study can be used by technical and functional stakeholders in finance domain while selecting open source LLMs for their use case and application. Now that we have had a look at the research gap, let's have a look at the data sets used in this research. We have 2 tasks considered for this research: question answering and sentiment analysis. FinQA dataset will be used for question answering. This dataset comprises of close to 7,400 records with data extracted from various financial reports. As we can see from the images, we have both the text and tabular data. The text before the tabular data is represented in the pre-text column. The text after the tabular data is represented in the post-text column. And the tabular data is stored in the table column. The data present in the financial report is not stored as it is in the data set. Let's say we have 10 sentences in the text before the tabular data. It will be stored as a list of 10 sentences in the pre-text column. Same holds true for post-text. Coming to the tabular data, let's say we have 5 records, as we can see from this example, including the header. It will be stored as 5 lists, with each list having an element which corresponds to the value in the table. This data cannot be used as it is to fine-tune the LLM. It needs to be converted into a particular prompt template which can be used to fine-tune the LLM. Let's have a look at that. The pre-text, post-text and the table columns have been used to construct the context in the final prompt. Necessary transformations have been applied to convert these columns into a format which can be used to fine-tune the LLMs. The LLMs will be questioned on the context which is present in the final prompt. In addition to this, the final prompt also has the instruction which describes the task to the LLM. It also has the actual answer. This final prompt will be used to fine-tune the LLMs. Now let's have a look at the financial phrase bank dataset which will be used to fine-tune the LLMs on sentiment analysis task. It has 2 columns, sentence and label. Sentence is nothing but a financial news text and label is its corresponding sentiment. Similar to question answering, it will be converted into a prompt format. Input text is nothing but it contains the sentence for which the sentiment needs to be predicted. And similar to question answering, we have the question followed by the actual answer, and this prompt will be used to fine tune the LLMs. Now that we have had a look at the data sets, now let's have a look at the research workflow. The first step in the research workflow is to load the datasets, and the next step is to convert it into a format which can be consumed by the LLMs. Then that dataset is split into train and test dataset, and instructions are added to the train datasets to convert it into an instruction tuning dataset. And the next step is to prepare the fine tuning framework. The optimal values are selected for LoRa and other neural network hyperparameters to construct the fine tuning framework. This fine-tuning framework will be used to fine-tune 3 LLMs, Llama 2, Mistral and Falcon, and the fine-tuned models will be saved for evaluation and inference. These saved models will be evaluated on the test dataset separately for question answering task and sentiment analysis task. For question answering task, exact match accuracy will be used as metric, and for sentiment analysis, precision, recall and F1 score will be used as metric. We'll go more into these evaluation metrics when we discuss the results. And finally, in the research workflow, based on the results, we present a thorough and comprehensive comparative analysis of the models. Now that we have had the look at the research workflow, let's look at a little bit deeper into the fine-tuning techniques used in this research. LLMs have billions of parameters, and performing full parameter fine-tuning will involve updating all of these parameters, and this is computationally expensive. Generally, the LLMs are built based on neural network architectures. Neural networks typically store their parameters, the weights and biases, in the form of matrices. Low rank adaptation is a technique which uses low rank matrices to represent the neural network weights and thereby reducing the number of parameters which needs to be fine-tuned. Let's have a look at this with an example. Let's take a matrix M, which is a 5 cross 5 matrix, which means 5 rows and 5 columns. This can be decomposed into two matrices, S and P, which is having a dimension of 5 cross 2 and 2 cross 5. This is possible because of a technique known as rank decomposition. Rank is nothing but the maximum number of linearly independent rows or columns. As we can see in the column M, there are repeating rows and columns. So this the original the rank of this particular matrix is 2, even though the dimension is 5 cross 5, which means that the original matrix M has 25 values. These 25 values can be represented by a dot product of the matrices S and P, which is nothing but the totally it contains 20 values. The LoRa technique goes a step further and states that the rank, the matrix can be represented by a rank which is even lower than the rank of the original matrix. This led to a significantly lesser number of values in the decomposed matrices, and this is particularly effective in case of LLMs, which comprises of billions of parameters. Let's again look at this with an example. Let's take a matrix C, which is 1000 cross 1000 matrix, which means it has 1 million parameters. And if we do rank decomposition using rank equals 8, it's get converted into two matrices, 1000 cross 8 and 8 cross 1000, which comes up to a total of 16,000 parameters. Instead of fine-tuning and updating 1 million parameters, using the LoRa technique, we can just update the 16,000 parameters. This leads to a significant cost savings in terms of computational resources. Due to the advantages of LoRa technique, this fine-tuning technique will be used to fine-tune the LLMs in this research. Now that we have looked at detail into the fine-tuning techniques in this research, let's have a look at the analysis and design of this research. Rank hyperparameter is the most important parameter from the fine-tuning perspective, as we saw from the earlier slide. So experiments were performed as part of this research to select the optimal value of rank. For other neural network parameters, hyperparameters as well, optimal values were selected, and this was used to construct the fine-tuning framework. Google Colab platform has been used in this study to develop the programming framework. The major advantage with Google Colab is that it provides compute resources, GPUs, required to fine-tune and evaluate the LLMs. Fine-tuning LLMs generally requires high-end GPUs, and hence Google Colab Pro Plus, which is nothing but a paid version of Google Colab, has been used in this research so that we have access to the NVIDIA GPUs like A100 and V100. Hugging Face libraries and packages has been used in this research to load the data, perform the fine-tuning, and save the models, and based on the saved models, evaluation was done on the test dataset. Now that we have looked at the analysis and design, let's have a detailed look at the results of the study. The models have been fine-tuned using the fine-tuning framework, and the fine-tuned models were used for evaluation. For the sentiment analysis task, precision, recall, and F1 score metrics were used to evaluate the LLMs on test dataset. The macro average F1 score has been used because this is a useful metric for imbalanced dataset as it treats all the classes equally. This is applicable for the financial phrase bank dataset because it contains close to 60% of records as the neutral sentiment. The charts show the macro average F1 score for each sentiment class, positive, negative, and neutral across the LLMs. As we can see from the numbers, all the macro average F1 score ranges from 0 to 1. If the number is closer to 1, it means the models have a very high predictive ability for that particular class. As we can see from the numbers, all the LLMs across sentiment classes have a very high F1 score. So the key interpretation based on these results is that all the models are showing very high predictive ability across the sentiment classes. Now that we have had look at the class-wise results, let's have a look at the overall results for the sentiment analysis for the LLMs. The macro average score of each of the sentiment classes has been averaged to get the macro average F1 score of the LLMs. As we can see from the numbers in the chart, all the three LLMs have very high F1 score. So the interpretation is that all the three LLMs have shown outstanding performance on sentiment classes. Another interpretation is that the Mistral and Falcon models have a perform slightly better than the Llama 2 model. Llama 2 has an LLM F1 score of 0.95, whereas Mistral and Falcon have a score of 0.97. Now that we have had the we have had a look at the detailed results of sentiment analysis, let's have a look at the results of question answering task. Exact match accuracy has been used to evaluate the LLMs in question answering task. Exact match accuracy will be 1 for a particular record only if the predicted answer is an exact match of the actual answer, or else it will be 0. So for the overall model, exact match accuracy will be calculated by considering the records where the predictions match exactly the answers and it is divided by the total number of records. So the exact match accuracy will vary from 0 to 1, and if the value is closer to 1, then the interpretation is that that particular model has shown outstanding performance in the question answering task. As we can see from the numbers, all three models have underperformed in the question answering task. The numbers for Llama 2 is 0.95 and Falcon it is 0.12 and for Mistral it is 0.33. Even though all three models have underperformed, the another key interpretation from these numbers is that the Mistral has scored almost twice the scores of Llama 2 and Falcon. Now that we have had the look at the result of the question answering task, let's have a look at the overall results. As we can see from the numbers in the table, all three LLMs have very high F1 score for sentiment analysis task, and all three LLMs have low scores for the question answering task. Based on these numbers, the three key takeaways are all three LLMs show outstanding performance on sentiment analysis task, and hence any of these LLMs can be considered for sentiment analysis in finance domain. All three LLMs underperform on question answering tasks, and this shows that open source LLMs have much scope for improvement in question answering tasks based on numerical reasoning. This could be a future avenue for research on open source LLMs. Mistral is the best performing LLMs among the LLMs considered because it shows excellent performance in sentiment analysis, and it scores almost twice that of the other models on question answering task. The findings and results of this study can be used by technical and functional finance domain stakeholders while choosing a particular LLM for their specific use case or application. Now that we have had the look at the overall results, let's look at the conclusions and future recommendations of this study. Based on the research and work done as part of this study, the aims and objectives were achieved and results were reported. The key NLP tasks and top open source LLMs used in this study were selected through elaborate literature review. The programming framework was developed to load the dataset, convert them into a format which can be used for fine-tuning, and performing the fine-tuning and evaluation. Thorough and comprehensive comparative analysis was performed and the results were reported. The result of this research showed that the performance of open source LLMs on numerical reasoning based on finance data was not up to the mark. The research, when it comes to the future recommendation, research can be conducted to improve the numerical reasoning capabilities of open source LLMs, especially in the context of finance domain. Future studies can also focus on exploring other open source LLMs which were not considered as part of the study, and also other tasks can be considered, and similar comparative analysis can be performed. That's it from my end about my thesis, and I would like to thank LJMU for giving me this opportunity. I would also like to thank my thesis supervisor, Dr. Dattatreya Parle, who has guided me and supported me throughout this journey. Thank you.